Lesson 1, Harder Mathematical Induction, Series Type. Now prove by mathematical induction that 1 times 1 factorial plus 2 times 2 factorial up to n times n factorial equals n plus 1 factorial minus 1 for n greater than or equal to 1. Now what we'll do, we'll start off and prove it true for n equals 1. So for n equals 1, the left-hand side is obviously just 1. The right-hand side is equal to, now this will be 2 factorial minus 1, which is, of course, 1, which equals the left-hand side. So this statement, we'll asterisk that, therefore the statement is true for n equals 1. Now what we have to do now is to prove the statement is true for n equals k plus 1, but first we'll assume it's true for n equals k. So assume the statement is true for n equals k. So 1 times 1 factorial plus 2 times 2 factorial all the way up to k times k factorial is equal to k plus 1 factorial minus 1. It's our assumption statement, which I'll label A. Now prove the statement is true for n equals k plus 1. That is, i.e. that is 1 times 1 factorial plus 2 times 2 factorial plus all the way up to now k times k factorial plus the next term along, which is k plus 1 times k plus 1 factorial, and that's going to be equal to, adding 1 to this, k plus 2 factorial minus 1, and we'll call that our proof statement, our P statement. Now you'll notice here on this side, this is virtually the same as the assumption statement, except for this one term. I'll just underline that. So that's the only thing different. So what I'm going to do, I'm going to add that term to both sides of the assumption statement, making the left-hand sides the same. Alright, let's have a look at this. So I'll add k plus 1, k plus 1 factorial to both sides of A. And I'll write all this out. So we get 1 times 1 factorial plus 2 times 2 factorial plus all the way along plus k times k factorial plus, and I'll make that a different colour so we can see what I've done, k plus 1 times k plus 1 factorial, and that's equal to, now this will be this one here, k plus 1 factorial minus 1 plus, now we'll just put that same colour in so you can see that all I've done is added that yellow bit to both sides of the assumption statement. So the left-hand sides match up, so if we can show that the right-hand sides match up, then we've proved the result. So therefore, I'll prove that and this is the only real bit of algebra you have to do, that this statement here, k plus 1 factorial minus 1 plus k plus 1 factorial is equal to k plus 2 factorial minus 1. So that must equal that for this statement P to be true. So look at the left-hand side. So the left-hand side equals, and I'll write this out again. I'll just rearrange that a little bit. K plus 1, k plus 1 factorial minus 1. So these minus 1's match up. So I'm just going to look at this. We can take out a common factor of k plus 1, k plus 1 factorial. And we'll have here, this is going to be 1 plus k plus 1. And of course that will give me, this is k plus 2 times k plus 1 factorial minus 1. Now, we know then that this must be equal to k plus 2 factorial. Because k plus 2 factorial is equal to k plus 2 times k plus 1 plus k, etc. So all that is your k plus 1, k factorial, sorry, it's your k factorial in there, minus 1. So that's equal to the right-hand side of our P statement. Therefore, the statement is true for n equals k plus 1. Standard procedure. Now, the statement is true for n equals 1. So, by mathematical induction, the statement is true for all n greater than or equal to 1.